how is this derived, this equilibrium law? And the equilibrium law is we take some generic equation, AA plus BB, dot, 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 goes to GG. So we go from reactants to products. It's HH, dot, 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 you know. Depends on how many products, how many reactants we have. And what we end up with is, you know, no matter how we start this reaction, that is, no matter what initial conditions there are, this could be initial concentrations, initial amounts, initial pressures, whatever the initial is, it always ends up at the same place, you know. So we could start off with, you know, all reactants or all products. And what's going to happen is there's going to be a change, which we call C, and then we reach the end of the reaction. The end of the reaction is called equilibrium. You know? So we put in any initial, and then we're going to always end up with the same equilibrium. And the same equilibrium can be defined by this. This is what we call KEQ. And there are different Ks for this one. For KEQ, we're going to have a ratio of products over reactants. And it's not as simple as this, you know, it's not just the products over the reactants, but we do some weird things to the products and reactants depending on what the coefficients are. The coefficients are the lowercase letters. Right? Now, it depends on how you express the initial conditions. Initial conditions could be in amounts. And so if you put in moles here, I'm saying this is a mole ratio or balanced chemical equation, how many moles of each we have. If you put in moles here, it doesn't work. You know, it's weird, but moles will not work. And what that means is you aren't going to, if we put in moles here, we aren't going to see this pattern with the final equilibrium moles. Instead, what works is molarity works, you know, and so if it's molarity, we call it K sub C. C just stands for molar concentration. Molar concentration. And then it works. So for example, if we do the molar concentration of the products, this would be square brackets G. This just means the molarity of G. And then we raise it to the little g power, then it works. And then H raised to little h, depending on how many products we have, divided by the reactants. A raised to little a, B raised to little b. And so just note here, moles, amount in moles does not work. I shouldn't say it does not work, because there are some cases where it works. You know, where it works is if the molarity on the top is equal to the molarity on the bottom. That is, let's say you have molar squared. If you were doing the units in molar squared, then moles would work. And so no, amount in moles in general does not work. Does not work. It only works in cases where the volume cancels out. That is, you have the same number of moles per liter on the top and the same number of moles per liter on the bottom. Then it works. If same number of moles per liter on top and on bottom. But oftentimes for reactions in general, you know, like this one will work because we'll just take a look at this one as an example here, this particular reaction. But for other reactions, you have, let's say, two reactants going to one product, or one product going to two reactants, or mismatch. Well, molarity and concentration are related. So if we have gases, then we have a choice. If we have solutions, we use aqueous here. If we have gases, then for the gases, what we do is we can express that in terms of molarity, or we can express that in terms of partial pressure. And so we have something called Kp. Kp is the partial pressure of G raised to little g, partial pressure of H raised to little h, dot, 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 over the partial pressure of A raised to little a, partial pressure of B raised to little b, dot, dot, dot. So it could be in terms of that for gases. So we can have any initial, this would be the change, this would be the endpoint of equilibrium. Equilibrium is where there's no longer going to be any more reaction, a net reaction, I should say, and we don't expect any change to occur. Okay, so for gases, we can relate the two, Kc and Kp, because they can come out as different numbers here. So if you use a Kc, you just got to make sure everything's in molar concentration. If you use a Kp, you got to just make sure everything's in atmosphere. Sometimes we're given molar concentrations in a Kp. Well, what do you do then? You have two choices. If you're given molar concentrations and we have a Kp, then you can convert all the concentrations into pressures. Or we can convert the Kp into Kc. That is, we can just use whatever. In fact, the relationship between Kp and Kc for gases, I should know. If we look at the ideal gas law, P is equal to nRT over V. N over V is just the molarity, moles per volume or moles per liter. Usually we express it in terms of liters. And so this is equal to the molarity times RT. Molarity is called M. So when we look at the Kp, we can go ahead and substitute. Kp is going to equal like G, the pressure of G. The pressure of G is going to be the molarity of G. But the molarity of G, we can express in terms of square brackets. So this would be the molarity here of G raised to little g power. And then we're going to have RT. Actually, this whole thing will raise to little g power, so I won't do that. And that would be the partial pressure of G raised to little g. Partial pressure of H raised to little h would be concentration of H times RT raised to H, dot, 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 over the concentration of A, RT raised to the A, then B, RT raised to the B. So for this, what we can do is we can factor out the RT out of this. If we factor out the RT, then what this is going to equal is just going to equal G raised to little g, H raised to little h, A raised to little a, B, little b. And then we're going to have RT. Then we're going to, G, on the numerator, we're going to have G plus H. Right? In the denominator, we'll have A plus B. And when we do this, I'm going to skip a step here. We're going to go G plus H plus dot, 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 minus A plus B plus dot, dot, dot. And then what we're going to call this is, we're going to call this delta N of gas. And so it's going to equal, in fact, when we look at this, this is this Kc, this first expression here. So that's going to be Kc RT, and the whole RT is going to be raised to delta N of gas. Where delta N of gas is the total moles of product minus the total moles of reactant gas. And so what we can do is we can use this equation here to calculate between the two. So if we're given one, we can easily calculate the other using this equation here. And I just derived the equation here. So for solutions, obviously there's no partial pressure for solutions. So for solutions, we use Kc. So in other words, for aqueous reactions, use Kc. For gaseous reactions, use either Kc or Kp. What if you have mixed? For mixed, and if you have solids and liquids. So if pure solids and liquids in reaction, then if pure solids and liquids in the reaction, then these are omitted from the K expression. These are omitted from K. They really aren't omitted. Because if you think about it, like a pure, you know the how much a liter of water weighs? Roughly? A kilogram or 1,000 grams. Do you know how many moles of water that is? 1,000 grams of water is, molar mass of water is 18 grams per mole. So it comes out to 55.5 moles in a liter of water. Pure water. So if you have pure water, let's say I had a liter of it. What if I had 500 milliliters? Is that going to change the molarity of the water? No. And the molarity or the concentration, it's pure water. So it's 100% water. Its concentration doesn't change. And so we don't include that. The same thing with pure solids. If it's a pure solid, it's 100% pure solid, and its concentration is not going to change either. And so this is the reason they're kind of omitted from the K expression. If you have a mix, that is, it's heterogeneous. Let's say you have solutions and gas. Then use KEQ. Now KEQ is the same thing as KP is the same thing as KC if you're dealing with just a homogeneous mix of reactants and products. But if it's heterogeneous, then what we do is this. In KEQ, what we do is we do the products. Now, if they're gases, we use the concentration, let's say G, like this, or we use the partial pressure. So KEQ, we'll use the partial pressure if it's a gas, and this if it's a solution. And so let's say G was a gas, then we use PG, partial pressure of G, raised to little g. Let's say H were a solution. If H were a solution, then we would use the concentration. So we'd have a mix, like for G, we'd have the partial pressure, for H, we'd have the concentration. And if all of them are gases, then all of these would be partial pressure, so KEQ equals KP if they're all gases. If all these are aqueous solutions, then KEQ equals KC. It's only when there's a mix involved that KEQ and KC and KP aren't the same.
Does that say solution gas at the bottom right?
Yeah, this says solution and gas on the bottom right there. So what we're going to do first is we're going to look at first coming up with a ratio K. The approach the blip case is a little bit different because historically when K's were first determined, they were determined experimentally. These came from observation. Nobody hypothesized this. Like for example, if you were to hypothesize all this, would you have come up with this? These types of equations here. So what is A? Have you heard A before? A, you might have forgotten A. Let's go back and look at A. Okay. Back in chapter 14, there's something called the stoichiometric concentration. So I can't highlight it. Can I? Something called the stoichiometric concentration. So for example, if you had, let's say, 1 molal or 1 molar sodium chloride, you'd expect to form 1 molar sodium ions and 1 molar chloride ions, right, independently of one another. That's called the stoichiometric concentration. But there's another concentration that's called the effective concentration here. The effective concentration is called the activity. And so the activity is just, effectively what is the concentration. And why wouldn't it be the same? So for example, here, let's take a look at some concentrations here. So if you had sodium chloride that just split up into 2 ions, and what you end up with is, let's say this is molality, you would end up with 2 molal ions. 1 molal from the sodium ions, 1 molal from the chloride ions. But what happens are these interionic attractions. You have ion-ion interionic attractions, which are like intermolecular forces. And so what that means is that the ions aren't completely independent of one another. There's some attraction there, and for a moment, they're paired. But they aren't bonded, And so this is like an intermolecular force, where we have ion pairing. If you have clusters of ions that are pairing with one another, then they aren't behaving independently, and therefore we don't really have 2 molal. In fact, it depends on how much of this ion pairing occurs. This is back in chapter 14. At higher concentrations, like this, it's 181, that means like 10% of the ions are kind of paired up. The rest are independent. At as we go more and more dilute, ion pairing becomes less and less of a factor. And so at infinite dilution, we don't expect any pairing to occur. And so because of ion pairing, the effective concentration might be less than what you expect based on the stoichiometry. And so activities are important for like colligative properties back in chapter 14. And so this is just a few paragraphs on this, which would be worth reviewing. Well, activities are given the symbol A. And as you get to higher and higher concentrations, things behave less and less ideal. You know, what causes things to, let's say, for example, deviate from ideal gas behavior? What are the two factors that cause the ideal gas law to fail? Pressure does, yeah. Do you guys recall the van der Waals equation? One of the things is very similar to what we just talked about, activity, these attractive forces. The attractive forces between the gas particles will make them behave less than ideal. So some particles are kind of sticky, like steam. You know, steam is not a very ideal gas because what happens with steam is you cool it down. You'd like to cool down steam to 0 Kelvin. You're not going to make it because what's going to happen is at 100 degrees C, what's going to happen to the steam? All the molecules are going to stick together to one another and it's just going to condense into a liquid. So that's not an ideal gas. And so this first factor in the van der Waals equation, A, deals with intermolecular forces of attraction. And you can see, like, for example, this propane has pretty strong intermolecular force of attraction, it looks like. Because it's got pretty big, pretty big London dispersion forces. Yeah. Whereas an ideal gas would have 0 intermolecular. Probably the most ideal gas, what is the most ideal gas you see? The most ideal gas would be helium. Helium is very weak. In fact, helium, you can almost get to 0 Kelvin. Helium will stick to one another at 4 Kelvin. It's very low. And so this is kind of similar to activity. So, you know, so when we're thinking about like pressure, you have your ideal pressure from the ideal gas law, and then you have the real pressure. The real pressure would be like the activity, you know, the real concentration. So why am I talking? Well, I'm talking about this is because your book's taking a different approach to this. The book is starting off with more of a theoretical approach. I didn't, because the theory came later. We're just doing an empirical approach to this. And so from theory, you know, we can derive these, you can derive this, the equilibrium law from theory, you know, except they don't really get into the theory that much. The theory comes from thermodynamics. Thermodynamics we haven't covered. It's going to be thermodynamics part 2. We're going to also derive it from theory, but not yet. It wasn't derived from theory initially. But anyway, the to be correct, the from theory, the equilibrium law uses activities, not concentrations. And so what are the activity for an ideal gas is just its pressure, basically. You know, as the gas gets more and more concentrated, that is, you know, higher pressures, smaller volume, that kind of thing, then it starts to deviate. And so as long as we're at fairly low pressures. Low pressures would be like 1 atmosphere. High pressure is like 100 atmospheres, 1,000 atmospheres. Then we're okay. We just use the pressures. It works. The activity for solutions, this is molar concentration. You know, as long as we don't go too high in concentration, we're okay. We don't have to deal with it. It's like, you know, it's like, why don't we do too many, you know, if you look at the pH range, the pH range is from what, 0 to 14. But 0 to 14 isn't the total range. You know, 0 is 1 molar acid, strong acid. 14 is 1 molar strong base, but we can have much higher than 1 molar. You know, 1 molar is not the limit. And so we could have negative pHs and pHs greater than 14. But the problem with those is once we get to higher and higher concentrations, then we get greater and greater deviations from greater and greater deviations from the stoichiometric concentration. You know, just whatever you predict from stoichiometry. So we should use activities here. And so the pH is actually the activity of H+. But we just, as long as we keep in the range 0 to 14, then we can go ahead and use the concentration. You go beyond 1 molar, then you probably shouldn't use the molar concentration. You probably should use the activity, you know. Because let's say you have 18 molar. Is it really going to behave like 18 molar H+, or are you going to see ion pairing occur, you know? You're probably going to see a lot of ion pairing occur, and that's going to lessen the impact of 18 molar. So anyway, this goes kind of theoretical. For pure solids and pure liquids, the activity is equal to 1. But here, like I said, I'm going a different approach. I'm going more of the approach that was, you know, observation to pattern to whatever. So the first thing we need to do is we need to be able to come up with a K expression, they call it. And so let's write some equilibrium constant expressions. And so let's take a look at number 1 here. If we look at number 1, based on these descriptions, write a balanced equation. Well, first off, we need the balanced equation because, you know, the coefficients turning power. And the corresponding Kc, okay, if it's Kc, then it's what? Concentration, right? Molar concentration. Carbonyl fluoride, COF2, decomposes into gaseous carbon dioxide and gaseous carbon tetrafluoride. I guess COF2 isn't the most stable stuff, so let's take a look at this reaction here. Now, this nomenclature, this is more organic nomenclature. You know, carbonyls is C double bond O in organic chemistry, and they just have 2 fluorines attached to it, like this. So maybe if you heat this stuff up, it decomposes into carbon dioxide and carbon tetrafluoride. So what is carbon dioxide? And carbon tetrafluoride, that'd be carbon tetrafluoride, CF4. It's tetrahedral. I'm not going to draw a tetrahedral, though. Probably should. We do that, so get more practice that way. Where the tetrahedral bond angle. This is called an sp3 carbon. sp3 carbons are tetrahedral carbons. sp3 hybridized like that. This is linear, this is trigonal planar. What type of reaction is this? I'm sorry? Redox? Oxidation reduction, you think? Okay, let's take a look at the oxidation states. So the oxidation states change here. And so what's the oxidation state of oxygen here? Oxygen versus carbon? -2. The carbon? Well, carbon versus fluorine, who's going to win? Fluorine. So carbon's going to end up with 0 electron. It's going to be +4. And the fluorines? -1 and -1 because it can take. Now let's look over here with CO2. What is it? Oxygen versus carbon, who wins? Oxygen, so oxygen is going to be -2. Carbon will be. So did it change? It went from -2 to -2, +4 to +4. It didn't change. Well, let's go over here to CF4. Did it change? Here, carbon versus fluorine. Fluorine wins. It's going to give an 8, which is -1. And carbon loses everything, which is going to be +4. So did it change? No. So it's not a redox. Redox, it has to change the oxidation state. Is this a metathesis? No, it's not a metathesis because there are no ions. Is this a Bronsted acid-base reaction? This is not a Bronsted, and via process of elimination, this means this must be a Lewis. This is a Lewis acid-base reaction here. In fact, well, how the heck is this going to react? Well, how the heck this reacts is there's got to be 2 of these here. Right? And I don't know how they're going to orient. Let's see how they orient themselves. Maybe like something like this. Let's go like this. So with Lewis acid-base reactions, we look for electron pair donors and electron pair acceptors. And so what we think is this. Maybe this can happen. Let's say this oxygen attacks this carbon. Now, why would that happen? Well, this carbon's going to be fairly positive. It's got all these electronegative atoms on it. This oxygen's fairly negative here. But then there's the octet law for carbon, and carbon cannot exceed an octet. And so this would definitely make it exceed an octet if there was another pair of electrons there, right? And so what else could happen in that particular instance? What else could happen is maybe what we could have is something like, this pair gets kicked out and made a lone pair, something like that. And as that happens, maybe, this pair comes down here in some kind of sequence, and eventually this pair breaks off and comes down here, and this goes up here, and then throw it into the bond somehow, something like this. And so we do it step by step. This is why Lewis acid-base reactions are kind of hard, because this is called a mechanism, how the electrons rearrange and in the orbitals, what orbitals they go into, if this breaks off, then that changes the hybridization of this to sp3, and then, does all this other stuff. So for Lewis, it's a bit more complicated, So you kind of want, and this mechanism, I don't know, is that correct or not? And there's lots of studies about mechanisms, for example, biochemists are very interested in mechanism, how things react. Okay. And so anyway, this is a Lewis acid-base reaction, and we're going to have 2COF2. This is gas, and this is going to go to CO2 plus CO4. So gas, this is the gas here. And so this is balanced. Okay, then what? They're asking for Kc. This is a gas, and so we could either do a Kp or Kc, it doesn't matter. But they want a Kc. So if they want a Kc, then we can do that. Kc for this is going to be the product concentrations raised. So if you know the concentration of CO2, it's going to be raised to the first power. And the concentration of CF4 raised to the first power divided by the concentration of COF2 squared. And that would be it. And so there's going to be some number here. So the next thing is, what is that number? You know, what is that number? And the number, we just look it up. You know, in a table, there's tables of K values. In fact, take a look on the right side of the middle chart. You see the right side of the middle chart there? At the heading, it says Ka. You know, that's the K value for acids. And so that tells us. We could take a look at some K values here. Here's just some small sampling of K values. And you can see they're all over the place. You know, you can have some that are just enormous, like this. 1.4 times 10 to the positive 83. You know, how big is that number? I mean, Avogadro is incomprehensibly large, but this is just phenomenally large, you know? And so what this says, it's all product. So if we have hydrogen and oxygen, hydrogen and oxygen forms an explosive mixture. In fact, just recently, unfortunately, there was a biologist, I think. Hydrogen is a pretty good reducer, and oxygen is a pretty good oxidizer. Well, I guess it wasn't super recently, 2017, 2016. There's a hydrogen explosion in a lab in the University of Hawaii. Unfortunately, the researcher lost one of their arms in this explosion. Hydrogen, a lot of gases. Compressed gases are always dangerous to work with. Look at that. It's amazing. It's a tank. Their gas tank. It's ripped apart. This is a hood. The hood has at least a hooded safety glass there. So they were using an electric pressure gauge. That's pretty gruesome. I didn't use electric. I used different kinds of pressure gauges, but they must have had a hydrogen leak. That's it. When you work with compressed gases, leaks are always an issue. Watch out for. But there's another researcher also in Hawaii who was actually killed in a hydrogen explosion. C&E News looks at all these lab accidents in detail. And then they have some kind of analysis on those. So this is a good source for that kind of stuff.
Are they just like lax with safety protocol, or is there something about
Sometimes, yeah.
Hawaii that
Ac-
makes it?
No, I mean, it's not just Hawaii, everywhere. I mean, there was a hydrogen explosion at UCSB when I was, well, actually before I got there, but just like maybe the year before I got there. It was a hydrogen explosion, it was glass. It was very weird because the blast sent a very thin shock wave, so like 3 feet off the ground, you could see around the perimeter of the room where all the debris hit against the wall. And fortunately, nobody was in the lab at the time. But if somebody got hit, hit their legs or something, debris, glass shards, which would be pretty nasty. Oh, there are a lot of academic labs and commercial labs are held to different standard by OSHA. So academic labs don't have as many safety because they're doing research, like cutting edge research, and so not everything is up to like if you have employees and then they need to be protected, but like graduate students and researchers, and postdocs. Well, obviously meth labs aren't held to any safety standards, but research labs are. But it's changing now because, at UCLA, I told you about the fire there, and the professor for that research group, I think, was actually arrested and was going to be charged, with criminal negligence, because he should have known. And so it's starting to. If they were in a commercial lab, yeah, they would have been responsible. Safety standards are quite a bit different.
Who pays for those damages? The school or the person that caused the damage?
The school.
Okay.
Unless they're doing a meth lab inside the. There was some chemistry. There are two chemistry. Did you hear about that? This is like straight out of Breaking Bad or something like that. But there were two chemistry professors who were arrested. Did you hear about that? Former Arkansas chemistry professor pleads guilty to making meth in college lab. This is 2019. They're going to pay. Roland was ordered to pay the college $150,000 in restitution. The amount they spent to clean the lab up, I guess. And so they're paying. I don't know, will they get the money? So this is very favorable reaction. And so what we see is a huge bias towards product, the numerator. Here, this is 10 to the minus 23. 10 to the minus 23 means there's barely any product. It's all reactant. And so this is like limestone. So we don't really expect limestone to decay. Now these Ks are for a specific temperature. If you change that temperature, it changes the K value. This is they say there's some the most important reactions in history. Have you heard of that? like their list, the 10 most important reactions in modern civilization. And this is one of them here. This reaction is really important in modern civilization because, you know, it's pretty much non-existent at room temperature. 298 Kelvin is taken as room temperature, which is 25 degrees C. But at 1200 Kelvin, it's 1.0. 1.0 means, yeah, you can get it to start producing some calcium oxide. And the reason this is so important is, and there's a really good documentary on this. This documentary is about Roman architecture and concrete. And still, you know, still a lot of people who work with concrete, you know, marvel at how good the Roman concrete was. You know, they're trying to make concrete. In fact, when I was at UCSB, there's a guy from the Navy, his Navy research lab, who was collaborating with our lab. He's using the NMR. We had the group I worked in was really big on spectroscopy. And there's a nuclear magnetic spectroscopy. So he's trying to use nuclear magnetic spectroscopy to look at the structure of concrete because, you know, Navy, they want to make concrete structures that can withstand erosion and weathering from the ocean, and they'll be in a marine environment. And so he's trying to improve on the concrete there. So that was interesting, but the Romans built some amazing, or synthesized some amazing concrete. So this documentary is pretty interesting because they're talking about, you know, how that came about. Well, the Romans were farmers or farming and had livestock so they could spend time doing scientific research. You know, if it wasn't that ability to have some time to do the scientific research, they might not have discovered this. And plus the Romans had coal and access to coal to get very high temperatures to do this. And then they could play around with products of this. And so this is a key ingredient for cement, which holds the concrete together. So this is one of the big reactions. If you look at this reaction here, this next one, well, actually, let's take a look. The first one, what kind of reaction is that there? This first one is a redox reaction. You know, elements are zero in elemental form, and it's +1 -2. It's redox, reducer, oxidizer. What about this second reaction? What kind of reaction is that? Would you say that's a redox reaction? Or do you say Lewis? You said Lewis, then that's actually, it's correct. This is a Lewis acid-base reaction here. It's not a metathesis, you know, ion combinations. It's not redox because none of the oxidation states change. It's +2, +4, -2, +2, -2, +4, -2. And none of the oxidation states change. It's Lewis acid base. So you do this thing with the, you know, with these arrows and the mechanism. I just grouped it all together at once here. But this is a big topic. You know, when we look at Lewis acid base reactions, we have to look at the mechanism for chemical reactions. So let's mechanisms. So we do what's called this electron pushing stuff. This is a very common mechanism here. This one too. So we got to draw out the Lewis structures, of course. Draw out the Lewis structures. We should also put the lone pairs out there. And it depends on how detailed these people want to get. So we have a lone pair attacking this sulfur. This is negative, this is positive. But there's, you know, too many electrons, so it knocks off the chlorine here. And things rearrange, and then this. And so we see a lot of these arrows to try to figure out how these things react. Lewis acid base type reaction. And then we look, you know, for Lewis acid sites and Lewis base sites, which there could be many, you know. And so that could be many potential reactions that we have. see if there are any others here. Yeah, some of these are simple. Others are more complex. Due to okay, I'm surprised I don't see it on more mechanisms. There's something they're kind of showing. Bonds forming with the blue dots. It's kind of interesting. Bonds breaking. Okay, let's go back to this. This one may be not so difficult, actually. Let's just take a look at this one here. What kind of reaction is this? This is redox. I'm going from +4 on the sulfur to +6 on the sulfur. So this is definitely redox. And this is going from 0 to -2. And so this is just oxidizing or burning sulfur dioxide. Sulfur dioxide forms when you burn like sulfur containing fuels. Like one of the big things is like low sulfur coal. Have you heard of low sulfur coal? Low sulfur coal because when they burn coal, let's say in power plants to generate electricity, it generates oxides of sulfur. And they used to not capture these oxides of sulfur. They would just let them out the smokestack. And then in air, the sulfur dioxide gets oxidized to sulfur trioxide. And then sulfur trioxide reacts with water in another Lewis acid-base reaction to form sulfuric acid, causing acid rain. And so this is the source of acid rain here. So this is an important reaction. It's not as big of a thing now because they have scrubbers now. So if they burn sulfur-containing coal, they treat the exhaust here by capturing any sulfur products. These aren't too hard to capture. And they can capture those and then separate those from the exhaust. So it's much cleaner burning. You know, everything's much cleaner now. It's like you know, there's the big push towards, you know, electric vehicles right now. So it's like what, 2036, we're supposed to be all electric, right? But I think, you know, as far as making a big impact on pollution and CO2 emissions or just pollution in general is to maybe have cleaner burning. You know, if we could get rid of some of the older cars are much more significant polluters than newer cars are. So I think, you know, push towards making newer cars maybe more affordable, then that would do wonders for air quality, I think. You know. It's just, you know, how do you generate the electricity? That's the issue. And the infrastructure for that electricity is very young. But if we look at this, this is 3.4. 3.4 means, you know, you got significant amounts of both. This is at the end of the reaction. At the end of the reaction, we don't have all products. We don't have all reactants. So if we look at these first two, this first two is pretty much all products. There's such a minuscule amount of reactants left over, probably don't care too much. So if this were Chem 1A, we just do regular Chem 1A stoichiometry. Now the second one, you know, a minuscule amount. I mean, 10 to the 23. 10 to the 23 is like Avogadro's number. It's like 100, 100 million trillion to something like that. You know, Avogadro, it's just huge. So this is It's so little CO2. I mean, if you had a statue, a marble statue, you aren't going to be worrying too much about this reacting. And so in Chem 1A, we'd probably say no reaction for this one. No. In Chem 1B, we could calculate what minuscule amount of product would form here. Or in Chem 1B, we could actually calculate what minuscule reactant would actually be unreacted. Although if you had a normal sample, it would probably be nothing. You know, you probably have to have a universe of this to actually measure any amount. But in this case, you know, you do the reaction, and the reaction is going to be a big mixture of both. You know, and so how do we? We definitely need Chem 1B stoichiometry. Yeah. Now, where do these numbers come from? These numbers come from measurement. You know, most of these Ks are determined experimentally. And so what they'll do is they'll do the reaction and take some measurements and see. Although these measurements would be very difficult. Maybe these came from theory. There are different ways we could get the K values. We'll talk about that. And then this one, you know, is this one, well, this is 10 to the minus 21, so there's barely any, barely any product. You know, this is taking just, let's look like graphite or carbon and water. And this is at 298 Kelvin. At 298 Kelvin, you put some graphite in water and pretty much nothing happens. You know? It's like you put pencil lead in water. Are you going to expect to form hydrogen gas when you put no. And so that's like 10 to the minus 21. You know, and so Chem 1A, we'd say, the pencil lead is not going to react with water. Right? Because equilibrium constant is so small. Now, at 1100 Kelvin, then you put the pencil lead in water, what are you going to see? Well, it's not going to be water, it's going to be steam. At 1100 Kelvin, you aren't going to have water, it's going to vaporize. And so this is called the water-gas shift reaction. This is a very famous reaction also because this reaction can generate hydrogen. But, you know, how much energy does it take to heat something up to 1100 Kelvin? You know, so there are hydrogen fuel cell vehicles driving around. In fact, you know, Torrance has these hydrogen filling tanks, one on 190th, one on Prairie. Have you seen those? Yeah. And in fact, Toyota was offering, it was very tempting to get it, hydrogen. And I know somebody, you know, who well, actually, I didn't know him. I don't know him very well. But he leased one of these hydrogen fuel cell vehicles. He's a chemist also. And he works in Irvine. And so this is one way to generate hydrogen, but it's very expensive. What are the other ways of generating hydrogen? They're all kind of expensive. Electrolysis, you know, you need, you know, a lot of electricity to do that. Electricity, pretty soon, are you wasting energy or are you conserving energy in that sense, you know? And so what a lot of people are trying to do is they're trying to generate using photoelectrolysis, that is, rather than generating electricity from a plug, they try to get it from the sun to electrolyze water. And so there's some progress there. In fact, C&E just had something recently on that I just now remember. What was it? What did they call it? Where they had pretty high efficiency, photoelectrolysis of water, C and E used. This was very recent. 2021. They had very high conversion rates. I'll have to find the article some other time. It didn't pop up. So that's one way that you could generate hydrogen. But one of the concerns I had, and I had talked to this guy about, is how can you be comfortable with a tank of hydrogen sitting underneath your car? Yeah,
They have vent ports. So versus a gas car, if you have a fire inside the engine, you can pour out all of the hydrogen in the engine versus in a gas car, you kind of,
Oh, okay, so it vents into the engine.
there's a vent out. So if there's too much pressure inside the engine,
Mm-hmm.
it just vents out. I've seen
But what happens if when you vent out, it ignites the
it
hydrogen?
ignites and it burns
Like a flame
like a
for,
flamethrower.
all right. Just don't stand in front of the end, basically.
I had a teacher who it happened to him on the road,
Oh, wow.
and he videoed it.
Wow, how
So
cool.
that's their like safety mechanism?
Yeah.
Oh, I didn't know that. But what this guy said was, he said he decided to buy it after they dropped a full tank of hydrogen from an airplane at high altitude. Did you hear about that? Yeah.
To test the,
To test the mechanical strength, and it didn't leak, you know. But you know, you got all the high pressure gas lines and other stuff. It's just that's interesting. Okay. But anyway, this is some reaction 10. So you can form some hydrogen there. We 10 doesn't sound like you're going to produce all that much hydrogen, does it? You know, if you have a 10, it's like a 10-to-1 ratio, right? But there's something called Le Chatelier's principle. Le Chatelier's principle is something I think we're looking at tomorrow in lab. Are we doing Le Chatelier's tomorrow in lab? Yeah. All right. What Le Chatelier's principle says is that okay, if we're at a 10 and we want hydrogen, what we can do is we can start removing the hydrogen from this. So if you keep removing the hydrogen, taking it away, then it becomes unbalanced. So let's say it's balanced like this, 10. But if you keep taking away the hydrogen, then it keeps trying to make more to reestablish that balance. And so that's called a shift. And so if we can take out the hydrogen from this reaction shifts to the right, and then we can produce more hydrogen. And so even though it's not very favorable, we can make it more favorable by removing the product. And so Le Chatelier says, if we have a system at equilibrium, then, and the same thing with this, you know, if you look at it, it's just 3.4. But what happens is the SO3 reacts with water. As the SO3 reacts with water, it forms sulfuric acid. And as the SO3 disappears, then it screws up the ratio. And so what happens is it shifts right to make more of the SO3. And we could do that. Same thing here, the CO2. If we remove the CO2, it could shift to right. But this reaction is so unfavorable. Even if we remove the CO2, it's going to be difficult to get going. So we're going to be looking at Le Chatelier's principle. In fact, let's take a look at Le Chatelier's principle, because once we hit this balance, so kind of going a little bit out of order, but we'll talk about tomorrow's lab. So here's the reaction here. The sulfur dioxide plus oxygen yields sulfur trioxide. And the Kc is 2.8 times 10 squared at 1,000 Kelvin. Usually we specify the temperature. If the temperature is not specified, then we take it at 298, just standard room temperature. I shouldn't call it standard, just normal room temperature. There's no such, I guess there's standard temperature. What's the standard temperature for gases? 0 degrees C. So look at that. And so here we have this equilibrium, and this equilibrium looks like it favors the products of sulfur trioxide, but this is like 280 to 1 kind of thing. But not exactly, because this is squared, that's squared, this is the first power. But it's sort of like that. Okay, then we put this in, and it's done reacting. We have the right ratio. So here, this would be the 280 to 1 kind of ratio here, with amount. And so we got more product than reactants. And now this is balanced. This is at equilibrium. There's going to be no more change. So one thing we could do is remove the SO3, but in this case, you know what? They're going to add more SO3. If you add more SO3, then we have too much SO3. It screws up the balance. So if we have too much SO3, what's going to happen is we're going to lose some of that SO3. So if we do this, we have 1 mole of SO3 plus 0.68. That gives us 1.68 moles of SO3. It's too much. And so it's too heavily product balanced. And so what it's going to do is it's going to drop down to reestablish a balance, the balance that we had earlier. But if you look at the new balance conditions, so we go from 1.68, so we're going to lose some SO3. So it's going to drop from 1.68 to 1.46. And then the SO2 is going to go up 0.32 to 0.54, and the O2 is going to go up 0.16 to 0.27. And so what we call this is a shift left. And the shift left is everything increased. So what happened was, rather than removing the SO3, we add more SO3. It screws up the balance, and then it shifts left to reestablish a new equilibrium. And the new equilibrium will have the correct ratio here, but we have more of everything, from the original, more of everything because we added that. And so we're going to look at, this is called perturbing the equilibrium. So we're going to look at perturbing the equilibrium here. So let's predict the effect of adding more N2. The constant volume equilibrium mixture of N2H2 and H3. So now this is all in equilibrium. We have the right K. I call it K. And so we add more N2. That means it's too much reactant. That means the denominator is too big. And that means it's going to shift right. And so the answer is this: it shifts right. It shifts right to convert some of the reactants to product to reestablish that equilibrium. Shift meaning it just forms more. So this is kind of a long one here. Let's look at this one. Calcination of limestone, decomposition by heating. So we take limestone or marble or whatever they use. Marble has some, I think, magnesium carbonate. But anyway, we want the calcium. Is the commercial source of quicklime, calcium oxide. Calcium oxide is called quicklime. Again, this is for concrete. After this equilibrium has been established in a constant temperature, constant volume container, what is the effect on the equilibrium amounts of materials caused by adding some calcium oxide? So if we add calcium oxide, what is that? That's a product, right? And what that's going to do is it's going to upset the balance, right? We're going to have too much product. If we have too much product, it should shift backwards. Basically, it's too product heavy. But this is very tricky. This is very tricky because, when we look at the equilibrium law, it's concentration or pressure. But what if we have a pure solid? If I add more, does it change the concentration? No. Or remove? And so when I add or take away calcium oxide, it doesn't change the concentration or the pressure, and therefore it's not going to have any impact. So adding some calcium oxide doesn't result in anything. Nothing changes, except you have more calcium oxide. If we add more CO2, that's going to change it because now we're going to have too much product, pressure or concentration, doesn't matter. So if we have more CO2, it's going to force this backwards. If we add more calcium carbonate solid, will that have any impact? No, that won't change anything. Okay, now what they're doing here is they're changing the pressure of everything. Okay, so we have different impacts here. Add or remove gaseous reactant or product. The effect of these actions on the equilibrium condition is simply that caused by adding or removing the reaction component as described previously. In other words, it's going to shift it one way or the other. If we add an inert gas means it doesn't react. And so if we add an inert gas to this here, let's say, I add more nitrogen to this, or add more helium to this. Does nitrogen or helium play any role in this? No. So if I add an inert gas, what's going to happen is the total pressure is going to go up. Because the total pressure is the sum of the partial pressure according to Dalton's law of partial pressures. And so if I add helium to this, the total pressure goes up, but nothing happens. There's no change because helium does not participate in this. But there's another way of increasing the total pressure. Another way of increasing the total pressure is if I squeeze the volume down or add more CO2. If I add more CO2, the pressure can go up, or if I squeeze the volume down, the pressure can go up. And so if I increase the pressure of this by changing the volume or adding more CO2, it's going to shift it left. Okay. And so let's take a look at what happens here. So I have a system at equilibrium here, which is the same equilibrium we had before. Now I'm going to squeeze this and increase the pressure of all the gases. If I increase the pressure of all the gases, what impact will that have? So that means I'm increasing the pressure of both the reactants and the products. So if you think of increasing both, then it should be no change because both the reactants and the products. And that's exactly what you see. You'll see no change unless you have different amounts on both sides. And so when we look at this one, which side has more moles of gas? Well, this is 2 moles of gas plus 1 mole of gas. It gives us a total of 3 moles of gas. 3 moles of gas at room temperature, which is 25 degrees C, and 1 atmosphere pressure occupies a volume of about 24.5 liters. And so altogether, we have about 75 liters of gas here on the left. I'm not doing an STP because we don't usually work at standard temperature. And so this is about 75 liters of gas on the left. On the right, it's 2 moles of gas, which is about 50 liters of gas. So if you squeeze this down, which side is more favored? You know, actually the right side is going to be more favored. So if we squeeze this down, the right side is more favored because the right side takes up less space. And so let's see what happened here. The right side of this is SO3. And so we started off with 0.68 moles, and then what did we end up with when we squeezed it down? We ended up with more. And the reactants here take up more volume. We end up with less reactant because we're squeezing it down. It favors. So this is the Le Chatelier's principle here is the smaller the volume, we're going to favor the side with fewer moles of gas. The bigger the volume, we favor the side with more moles of gas. So we can easily reverse this. The way we can reverse this is just lift the plunger up. If we lift the plunger up, then that's going to increase the volume, and take a look at what happens. It shifts to the side with more moles of gas. So it just goes backwards. Okay. In other words, the reactants. This is, but what if we have the same number of moles of gas on both sides? That is, let's say we had 75 liters on the left and 75 liters on the right, then is one side favored over the other? No. And so there's no shift. We have the same number of moles of gas. There's some mathematics involved with this that we could do, but I'm not going to do it here. Let's look at it here. An equilibrium mixture of N2, H2, and NH3 is transferred from 1.5 liter. So we're going from 1.5 liters to 5 liters. So we're increasing the volume. In which direction does the net change occur to restore? So the first thing is it upsets the equilibrium here. But when we look at this, is a redox reaction here, forming ammonia. Which side has more moles of gas? Which side has fewer moles of gas? Yeah, over here we have 4 moles of gas. Over here we have 2 moles of gas. And this is what we call, what is delta N of gas? Remember delta N of gas? Delta N of gas is the change in the number of moles of gas. And so we can do it easily here. We went from 4 to 2. What was the change? 2. Was it a -2 or +2? It's a -2. We lost 2 moles of gas. So that would be delta N of gas here. That's for the Kp-Kc relationship, when we calculate. So that means Kp and Kc are not the same. Now, if delta N of gas is 0, then Kp and Kc are the same thing. They're going to give you numerically the same value. Okay, going back to this one, we make the volume bigger, which is going to favor the left side or the right side? Left side, so this shifts left. It's going to favor the left. Okay, here, the reaction N2O4 goes to two NO2s. This is the Lewis acid-base reaction here as well. Is at equilibrium in a 3-liter cylinder. What would be the effective concentrations if the pressure was doubled? So we double the pressure. That is, the cylinder volume were decreased to 1.5 liters. So we're doubling the pressure of everything by reducing the volume, which means it's going to shift left. How about this one? How's the equilibrium amount of H2 produced in water gas shift? This is the water gas shift reaction we talked about earlier, affected by changing the total gas pressure or the system volume. So when we change the total gas pressure, what's going to happen? Let's say we increase the volume or decrease the volume, what should happen? No change, right? Because we have 2 moles of gas, 2 moles of gas. That means delta N of gas is 0. When delta N of gas is 0, then Kp and Kc are the same thing. When delta N of gas is not 0, then Kp and Kc give you numerically different number values. The following reaction is brought to equilibrium at 700 degrees C. Indicate whether each of the following statements is true, false, or not possible to evaluate from the information given. So this is H2S is hydrogen sulfide gas, and the methane. So what kind of reaction is this? What does it look like to you? Redox, yeah. This looks like redox. This is +1 on hydrogen, +1 on hydrogen. This is 0. So this is some kind of redox. So hydrogen gained some electrons. What did it gain from? Looks like the carbon, perhaps. We have to analyze it a bit more. Indicate whether each of the following statements is true, false, or not possible. So if the equilibrium mixture is allowed to expand into an evacuated larger container, what will happen to hydrogen? Yeah, it's going to increase because this is 3 moles of gas. This is 5 moles of gas. So larger container is going to favor the products. It shifts to the right, making more hydrogen. If several moles of argon gas are forced into the reaction container, the total pressure will increase. For sure. The amounts of H2S and CH4 will increase. Is that true or false? This is false. Because does argon participate? No. Nothing happens. So these pressures all stay the same. The total pressure increases because of Dalton's law, partial pressures. If the equilibrium mixture is cooled to 100 degrees C, the mole fractions of the 4 gases will likely change. Okay, now, what happens is, when we change the temperature, that changes K. That changes the equilibrium constant, K. And so at different temperatures, we have different K values. That's why when we do these K values and measure them, we have to measure them for a given temperature. And shouldn't change that. And so, so yes, this is true. But then again, we don't have that much information regarding this, but most likely it is true. In fact, it is true. This is going from 700 to 100 degrees. If the equilibrium mixture is forced into a slightly smaller container, the partial pressures of the four gases will all increase. This is kind of tricky because if we go to a smaller container, it shifts it to the left. But what that means is that all the gases will change. You know, when we shift, because the products will get smaller, the reactants will get bigger, which is going to change the pressure. And so this is actually true. You know, just looking at it in general, it's true. There's another sister problem to this. The other sister problem is like this. The other sister problem is that if we add SO3, then the amounts of SO3, SO2, and O2 will all increase. Now, that's a bit tricky because it depends on what you compare it to. If you compare it to SO3 initial, then yes, we do see an increase because it went from 0.68 to 1.46. But if you compare it to SO3 after addition, which is 1.68, then the SO3 actually goes down and the other two go up. And so it depends on what they're using as a reference point. If you're referencing the original equilibrium, then yes, everything goes up. If you're referencing after the addition of SO3, then no, SO3 is going to go down. And so that's a trick question that people get sometimes on multiple choice tests that I've seen. Okay. Now what happens with temperature? We can make an even bigger prediction with temperature. If we raise the temperature, then the equilibrium mixture shifts the equilibrium condition to the direction of endothermic reaction. Lowering the temperature causes a shift in the direction of exothermic. So you think about melting ice. Is melting ice endothermic or exothermic? In other words, do you have to add heat to melt ice or do you have to remove heat to melt ice? You have to add it, so it's endothermic. So you think about adding heat will shift it in the endothermic direction. Removing heat is important. That's what a freezer does. A freezer removes the heat in order to freeze water and form ice. Now, this is not a shift. The previous shifts we talked about were the K didn't change. In this case, what we're looking at here is the K actually changes. When we change the volume, when we change the pressures, when we change the concentrations, K does not change. We just upset the balance. Here, the balance is fine, but we change the temperature, which changes K, and now we're no longer in balance because K increases. K increases as temperature increases for endothermic reactions. And for exothermic reactions, K decreases as temperature increases. So let's just apply this. Okay. Oh, okay. Sorry. What time we go till 11:10? Okay. Yeah. Thanks for that. All right. So